So we were talking in our previous lectures about formation of planets, the cloud of gas swirling together to make the protostar, the disk that then becomes the cloud of gas, or the disk that becomes the propellant, which then becomes the birthplace of all these planets. And so we talked about how you find the planets. As a planet goes around a star, it causes the star to wobble a little bit. If it's wobbling towards us or away from us, there's a Doppler shift, blue shift or red shift, depending if it's coming towards you or away from you. And so with that, you would actually then be able to find it if you can measure the spectral line. The spectral lines would go back and forth in the spectrum. And so as you see the spectral lines go back and forth, you could measure how long it takes to go back and forth. If you measure how long it takes to go back and forth, then you could figure out the orbital period, similar to what you do in the binary star lab. And so you'd find the orbital period. Kepler's laws would then let you work backwards to figure out a couple other things. You'd find the total mass of the system. So then you have the mass of the star plus the mass of the planet. By measuring by knowing the type of star it is, you know about the mass of the star, so that would allow you to figure out how long that would tell you, figure out roughly about the mass of the planet. So then you've got, if you get the mass of the planet, you can sort of guess what kind of planet it is. If the mass of the planet is like Jupiter size, it's probably going to be a gas giant. And so that gives us this basic sort of idea. And that's the way we're gonna approach this. And so that was finding planets using this radial velocity method. So the radial velocity method was using the Doppler shift. Another method of finding planets, however, is what we call transiting. A transit is the term that we use for passing in front of something. So a transiting exoplanet would be if it's lined up just right, the planet would actually pass in front of the star. When it passes in front of the star, since the planet doesn't shine, the light of the star drops off a little bit. So it'll drop by a fraction of a magnitude. And so that's measurable with modern technology. And even amateurs can measure this. Amateur astronomers have actually found exoplanets by doing this. And so what you do is you'd watch a star and find this dip. Now, just finding the dip doesn't mean it's a planet. You've got to find the dip again as the planet goes around. Now, once again, that means this is very sensitive to planets that go around quickly. Because if you're watching a star, day and night, different parts of the world watching the star, you'd have to watch the star day and night for years and years and years to find this sort of dip. So that'd be very difficult to do for planets that are further out. Remember, in our own solar system, we have some planets that take over 100 years to go around. So there's no way of finding something like that. Not this way of doing it. So this is also fairly sensitive to fairly close planets. But you can see small planets go by. Well, sort of. You can see small planets go in front of a small star. If a small planet went in front of something like the sun, so in other words, if Mercury or Mars went in front of the sun, it wouldn't dim out very much light. It might be hard to see that. But you could see Mercury or Mars go in front of a red dwarf, because the red dwarf is so small that it would actually block an appreciable amount of light. And so an example here, HD 209458, a planet went in front and it dimmed out. And so these are actually several data runs here, so it's reproducible. NASA launched a spacecraft called Kepler back in 2009, and the Kepler spacecraft was designed to just look in one direction in space at a whole bunch of stars and wait and measure all those stars continually to see planets possibly go in front. As they were looking at all these stars, they found about 5,000 of them had these dips in light consistent with planets. Since then, about half of those have been confirmed to be actual planets. And some of them have been in the right distance to what we could consider habitable zone. We'll talk more about that later. They're not really habitable planets. But of the 145,000 stars studied, about 5,000 of them. Now, let me point out, conditions had to be exactly right. In other words, that means the plane of those planets' orbits has to be lined up exactly with the solar system. That's statistically very unlikely. So if we can find, again, only about half of those are real or confirmed detections. So even if we only talk about 2,300 or so, that's an enormous percentage, enormous number, considering the low chance of this sort of alignment happening. So that would suggest that these planets are very, very common around stars. And some of these are actually about Earth-sized. In fact, by extrapolating the Kepler data, we probably would have billions of Earth-sized planets in the galaxy. So this is capable of detecting smaller planets. Now, a lot are Earth-sized, but a whole bunch of them are in this size range here. So we've got roughly Earth-sized planets. We have Mars-sized planets. Now, Mars and Mercury-sized planets are still really small to try to find, even by this technique. Though there are new spacecraft being launched that will have the ability of finding planets, that small. Far fewer of the gas giants were found by Kepler. Now, there's several reasons for that. One could be if the gas giants are out where they're supposed to be in the outer solar system, then they don't go by very often. And so Kepler was only able to look for a few years. And so that means that if the planet only goes by once every 10 or 12 years, Kepler might have completely missed it. Or it might have gone by just one time and not a second time, which would be necessary for confirmation. So it's no huge surprise that gas giants were not as detected. What was a little bit odd was that there were a bunch of planets detected. In fact, the most common kind of planet detected is bigger than Earth by a little bit, what they call super Earths, or a little bit smaller than Neptune, like dwarf Neptunes or sub-Neptune size. And so that turned out to be the most common kind of planet. Now, again, some people suggest maybe that's the most common kind of planet that exists. I'm not willing to make that call. I still think this could be a Malmquist bias sort of thing, that we are not seeing as many of the gas giants as probably are actually out there, partly because of the difficulty in finding them because they don't go by very often, and we're not seeing as many of the really small planets as are really out there, possibly because they are simply harder to find because they are dim. We do have new satellites being launched, astronomical satellites, which may be able to find these smaller planets. So, question, are the super Earths and mini Neptunes the oddities, or is the solar system odd? And the answer is we can't answer the question. We don't have enough data. The way that we find these things is much more sensitive to those sizes of planets. So that means we are still having a tough time, even with a Kepler spacecraft, it would have a tough time finding our solar system. The other thing that the Kepler spacecraft found was more planets around red dwarfs than any other kind of star. And I saw some graduate student once somewhere in an interview saying that that was indication that red dwarfs preferentially have planets. And I'm thinking, well, no, it's not. It's just because there's more red dwarfs than any other kind of star, so that's why you find more planets around red dwarfs. So I don't think that was indicative of anything other than that red dwarfs are common, so you see more red dwarfs. So that statement I don't think is really fair either. But we have one technique, the technique of finding extrasolar planets by Doppler shift. That's sensitive to big planets up close. The other method, transits, can see the smaller planets, but it's also insensitive or difficult to see big planets far. Okay. What about actually seeing a planet? Well, they're dim. They reflect sunlight, reflect starlight, so you have this tiny dim speck next to a star. And so that makes picking it out really hard. Nonetheless, that doesn't mean it's impossible. So this is actually a brown dwarf, so it's not really, it's a failed star, and something was found about 55 AU out from it, something that is about 3 or 4 times the size of Jupiter. So that's too small to be another brown dwarf, so that's got to be a like giant Jupiter planet out here. So that means brown dwarfs, things that form just like stars, can also have planets orbiting them. Again, GQ Loopy has an object way out here that's too small to be a brown dwarf, so it's probably going to be a Jupiter-sized planet. And in fact, in the direction of Taurus, there's actually an object that looks like it's been kicked out from a protostar. And so this is possibly a planet being kicked out. Remember, we said that if Jupiter and Saturn form really closer together than they currently do, Jupiter would move in closer and Saturn would have moved out further. It is possible that that could kick a planet out of a star system, either directly or indirectly. Either get kicked out, or if Saturn moved really far out, it could kick something like a Neptune planet further out of the star system. And so it is possible there are in fact planets kicked out of the star system. Well, that would mean you could actually have planets just flying around the galaxy. And in fact, there are some. We found about a half dozen of these free-floating exoplanets out there. There's likely vastly more than just that half dozen, because these things are super hard to find because they're super dim. They're just little cool things that just barely give off any infrared light at all. So they would be very difficult to find, which means there are several that are out there, which actually raises an interesting question. Could any of them be captured by another planet, or another star rather? Well, maybe so. Maybe planets could be captured by other stars, and so maybe a star that was a planet that's formed around one star could be found orbiting another star. So then raises the question: are any of the sun's planets captured planets? Well, there's no real evidence that they are. Well, could another planet enter the solar system? And yes, it could. What would that do to the planets that are already here? It'd be really bad, potentially. The gravity, if it's a big enough planet, could disrupt the orbit of the other planets. And since we're on one of those planets, that could be bad for us. Or could one even collide with another planet? Well, yeah, actually, that's even a possibility, too. It'd be highly unlikely, but it is a possibility, which is interesting because there are actually a couple of sci-fi stories. One called When Worlds Collide, in which a movie was made out of it, too, in which a planet collided with the Earth, and the scientists saw it coming, and they evacuated scientists and other people from Earth to go live on the other planet, which was going to go into an orbit around it was a binary planet that was going to go around the sun and take the place of the Earth. So anyway, but that was a sci-fi story. But yeah, there are free-floating exoplanets that have been found out there, and so that does raise some interesting possibilities.